All right, we have one of my favorite topics today. Actually, we get to talk about limits. Limits are fun. Limits are a pretty important idea with calculus. Remember, we've been talking about slopes of secants and slopes of tangents and trying to make the secant closer and closer to a tangent. And so last lesson we were talking about how if we made that value of h, which was our run when we were looking at our secant, if we made it smaller and smaller and smaller, our secant would become closer and closer to a tangent. That idea is what we're going to need as we continue in calculus. So we need to talk a little bit more about a limit, and we'll have to do some calculations, that sort of thing. So just to get us started, thinking about this idea of things going on for a while. So consider this little sequence, 1, 2, 4, 8, 16. All that's happening there, of course, is that the numbers are doubling each time. So what happens as they continue? Well, first of all, we have to recognize that they're going to go on for a while, right? 16, I can keep doubling numbers. So is there ever a point where I can stop doubling numbers? No, we can keep going forever. So that's that idea. Then this is going to keep getting larger and larger and larger forever. So this is where our infinity idea starts to come in. We say this sequence gets bigger and it gets closer to infinity. So here's the tough one then. Is infinity a number? And so that's an important question. The answer is no. And infinity isn't a number. Infinity is just an idea. It's this concept that things can go on forever and ever and ever. So infinity, we're going to see it a few times today. And we're going to have to be really careful with the way we write down the notation. The infinity symbol, in case you're unfamiliar with it. Looks, that's not my best effort. That's not my best effort either. Anyway, it looks about like that. Just a little, kind of like an 8 turned sideways. It's not a number. It's a symbol that's representing the idea of continuing on forever, but not a number. You can't have something like infinity plus 1. Okay, it doesn't work. This second one is a little bit more interesting. Just a grade 11 idea to point out, because I think it's important you remember these things. The first word up here I used was a sequence, and it's a sequence because I have commas. So a sequence is simply a list of numbers. Now I've got the word series, and it's a series because we are adding numbers together. So if I start adding these up, 2 plus a half plus 0.25 plus 0.125, and of course you have to notice the pattern still. I'm not just picking random numbers there. Each number in that series is the number before it divided by 2. Right? 2 divided by 2 is 1. 1 divided by 2 is a half. 1/2 divided by 2 is 0.25. So think about that one for a second. If we were going to add all of those up, what would happen? And this is I like this one because you're adding up an infinite number of numbers, right? That list goes on forever. But eventually we're adding in really, really small numbers, right? 0.125 is pretty small, and that's only the 5th term in that series. So by the time I get out to the 10,000th term, for example, you're still adding something, but it's very, very tiny. So what sort of an impact does that have? And this is it's a tough one to see. Maybe I can kind of represent it with a number line. This is going to be 0 here. It's going to be 4. I don't know, depending on how much time you've had to think about it, you already know why it's 4. If I start adding these up, this is going to be 1, 2, 3 there. If I start adding these terms, so the first number would be 2. Right? So I start with 2. That's just the first term done. And then I add one more. That gets me to 3. And then I'm going to add one more. That gets me to 3.5. It's right there. And then I'm going to add one more. That's a quarter. So now I'm at 3.75, which is about there. And now this one gets a little bit harder. It's 3.75 plus 0.125. That's 3.875, I think. If I did that decimal in my head right. That goes to there. Okay. And now it gets a little bit harder to show on the number line. But what I want you to notice is every time I put a new point on there, I'm getting halfway closer to the 4. So if you think of the distance from 0 to 4, 2 got me halfway from 0 to 4. And so now I'm at 2, and I'm going to add 1 to that. Halfway between 2 and 4 is 3. And now I'm at 3. So I'm going to go halfway between 3 and 4, which takes me to 3.5. And then halfway between 3.5 is 3.75. And then the 3.875. And after that, I should just cut in half and cut in half and cut in half and half and half over and over and over again. But if I do that, seeing this pattern, I keep getting halfway to the 4. I never get to the 4. So we say this sequence, excuse me, this series, if we add them all up, it gets closer and closer and closer to 4, right? The total will never be above 4. It will also never be equal to 4. And this is the tough one. It's going to get really, really close to 4, but never get there. Okay, keeps going closer, 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 but I can never quite get to 4. I can get as close as you'd ever want me to be, but I can't quite get to 4. Okay, that's a tough idea. It's a tough idea. Okay, close to 4, but not quite. That's a limit. We're getting really, really close to something, but we don't actually need to get there. This is also a fun one. There's a visual idea. We have to remember what the word regular means. It says a regular polygon. A regular polygon is a shape that has all equal sides and all equal angles. So an equilateral triangle, a square, I've got a regular pentagon there. If I start increasing the number of sides, what will happen to that shape? So I'm going to go to 6 sides and then 7 sides and then 53 sides and 184 sides. What does the shape start to look like? And the more and more that you add, the closer this comes to approaching a circle. Now, is it ever a circle? No, because I'm saying it has a certain number of sides, right? Eventually it's going to have 3 million sides. Is that a circle? Nope. But is it going to look like a circle? You bet. So notice the way I've worded that here. It says in a regular polygon with n sides as n approaches infinity. And I've used the word approaches, trying to say it's getting closer and closer to something that you can't reach. The n-sided polygon approaches a circle. It's not equal to a circle, right? It's getting closer and closer to one. So we're going to have an interesting time dealing with this approaches, this idea of getting closer and closer to something versus being equal to something. And in some cases, honestly, we're going to be using the same symbol. We'll sometimes use equals, even though in fact, we're not equaling something. We're just getting closer and closer and closer. This is a fun one to think about, and I'm not going to dwell on it right now because I want to move on, but just this idea of, is there actually such thing as a curve then? I'm trying to make a circle here or get closer to a circle by having an n-sided polygon. If you took a curve, for example, if you use say a computer program to draw something, if you used your zoom tool and started to zoom in, would it actually be a curve? Or could you zoom in far enough so you could actually start seeing a whole bunch of straight lines put together that made it look like a curve? Right? Is the curve really there? And then in that case, is there actually such thing as a circle? Is a circle a real thing? I don't know. Fun math stuff to play over. Here's another one. It says consider the sequence 2, 1, 1/2. That's the same sequence we just had, right? Except this time I put commas instead of addition. So that means I'm not thinking about the total here. I'm just thinking about a particular term itself. So as n approaches infinity, Tn, so that's the nth term. N is approaching infinity, right? So a term all the way down the list, as far as we can go. We just keep going. What does this last term, even though there isn't actually a last term, what's it getting closer and closer and closer to? Well, in this case, it's 2 to the n, right? 2 to the n is approaching infinity, so n is going to be a really, really big number, which means 2 to the n is an even bigger number. But then I'm going to divide. I'm going to go 1 divided by a really, really big number, and that's going to be a really, really small number. It's going to be something close to 0. So we just write Tn approaches 0. Will it ever be 0? No. It can't get to 0, but it can get really, really close. And that's our limit idea again. Getting really, really close to something, but not quite getting there. Here's some graphical stuff. So the graph of f of x shown below. That's our 1 over x graph. It says as x approaches infinity, and by the way, we can write this as well. We can write negative infinity if I want to go to the left. So in this case, it says as x approaches positive infinity, that means my graph is going this way. What's happening to the value of f of x? F of x is the y value, right? So as x gets really, really big, the function itself gets really, really close to 0. It's getting really, really close to the x-axis. It's actually negative the whole time. Right? It's always a negative number, but it keeps getting closer and closer and closer to 0. The way we actually write that, here's our notation. We're using just LIM for limit. And underneath that, we say x approaches, that little arrow there is for the approaches, negative infinity. And we're doing that limit for the function f of x, and the answer that we get is 0. So here's where we have to be really careful with our use of the symbol equals. I'm saying the limit is equal to 0. Does the function ever equal 0? No, it does not. But I'm not talking about it actually equaling 0. I'm talking about this idea of the limit. I'm saying, what do we get close to? Because I'm saying, what do we get close to? The answer is 0. I get closer and closer and closer to 0. I just never quite get there. Example 2 is a tough one. What happens as we approach 0? So if I'm approaching infinity like I just did there, that's fine because we're just going at it from one side. But as I approach 0, I can approach from two different sides, right? I can go this way, get really, really close to x equals 0, and go up. Or I can get really, really close to 0 from the right, and the graph's going down. So we're either becoming a really big positive number or a really big negative number. But because it's going in two different directions, what we actually say for this one is we say that this limit does not exist. And we'll talk more about this one a little bit later. By the way, sometimes your short form for that will just be DNE. You'll see that occasionally. So that limit there doesn't exist, and it doesn't exist because it's going to two different spots. It's going to positive infinity and negative infinity. I'm going to try these couple here. Not too much here, actually. This is kind of a boring graph, but you needed to see these as well. So there's our function. I guess I haven't actually labeled it, but let's call this function f of x. As we approach negative infinity, that means our graph is coming along here, is going further and further to the left. X is becoming very negative. The function itself is now heading upwards. So the graph is going to positive infinity. I don't really need to put that plus there, but sometimes it helps to distinguish. So that's one. That's one thing we can do. We can approach negative infinity. What if we're approaching 2? So we're getting closer and closer to 2. So I can come at it from two ways, right? I can come at it from this way. I can come at it from this way. We don't have the same problem that we had before, though. In that previous graph, that 1 over x graph, one side's going up and one side's going down. They're not meeting. This one's meeting. And I don't know, the graph's not perfect, so I'm not exactly sure where we're heading to, but right at 2, it looks like the graph's getting closer and closer to, well, it's a little bit under 0.5, maybe 0.6. Now what's interesting about that one, I'm saying the limit as we get really, really close to 2, the graph gets really, really close to about negative 0.6. With this one, does it actually get to negative 0.6? It does. Right? This time it's going to go through there. So this limit gets closer and closer to 0.6, and if I actually did go all the way to 2, we would actually get there too. So this is as I say, this is a much more boring limit. Take a look at the next one. As we approach 0, we're coming here, right? As x gets closer and closer to 0, the graph's getting closer and closer to that point right there, which is, around 0.3. Oops, lost the decimal. Not a very exciting example, but that's what the limit's approaching, right? As the graph gets closer and closer to an x value of 0, the function itself is getting closer and closer to a y value of 0.3. If we get closer and closer to negative 2, it's this way, our graph gets closer and closer to 0. And it reaches 0. That's not what the limit part means. When it says the limit, it's just saying what are we getting closer and closer to. Very important definition. Make sure you got this written down. You will need this. We say that a limit exists if the following three criteria are met. The first one there says the limit as x approaches a, right there, but it's got that little negative written above it. The way we would read that is we would say the limit as x approaches a from the left. And so the reason that negative sign is there is it's as if it's coming from the negative side of our grid, right? So it's coming from the left, coming from the negative region of our number line. Whereas the next one, this one's going to be as x approaches positive a, or as x approaches a from the right, I should say. That's the way we'll read it. Now, what it's saying there is that you need those two limits to both exist. Existing is tricky. We'll talk more about that still. The limit has to exist, and the limits have to be the same. So if you're coming at a particular number from the left-hand side and you're getting closer and closer to something, and you're coming closer and closer to something from the right, I need both of those values to be the same. And I'll show you what I mean when we look at this example. Here's our example right here. Determine if the limit exists. So the limit as x approaches 2 of this function. Well, the first criteria was I needed the limit as x approaches 2 from the left to exist. So here I am approaching from the left. I'm approaching from the negative side over here. I'm coming up, getting closer and closer and closer to x equals 2, and I'm going to get closer and closer to that point right there. Right? I'm getting closer and closer to a y value of 2. But then the second criteria was, what if I approach from the right? Does that limit exist? Do I get an answer if I come in from the right-hand side? And I do. And I come in and I get really, really close to a value of 3. So the limit from the left is 2, the limit from the right is 3. But do those limits exist? Or excuse me, are those limits equal? They aren't. So I write this. The limit from the left does not equal the limit from the right. Therefore, the overall limit does not exist. Okay. So my left-handed limit existed, it worked. The right-handed limit existed, it worked, it approached 3. But from the left we were approaching 2, from the right we were approaching 3. It wasn't approaching the same thing. So overall it didn't work combined. Get rid of that guy. Let's try this one. Okay, something to notice there. It's a little hard to see. I've got a little open circle. That's a hole. So do you remember what a hole is? That means right there is no point. Okay, right at 2, 2, no point exists. Okay, does that impact things? So I'm still approaching 2, but I have a slightly different graph this time. So as I approach 2 from the left, getting closer and closer and closer here, I'm getting close to that hole. But remember, it's only exactly at 2, 2 where there's a hole. So I'm getting closer and closer and closer to it. Means I'm getting closer and closer to a y value of 2, aren't I? I mean, the fact that it's not there doesn't matter. Because when I do a limit, I don't need to get there. I just need to get really, really close. Same thing from the right. If I come in like this, I get really, really close. And I'm still approaching 2. Even though there's a hole there. So there is a gap, but the limit exists because both the left and the right are approaching the same thing. So overall, the limit's 2. That one worked. A little bit tricky because it's got a hole in it, so it's not exactly what we were expecting. The last one for us. This is your advanced functions, I suppose. Sort of, just because we use a table of values, and I think you did a lot of that in that class. Determine the following limit exists using a table of values. This one is not very exciting, so I'm going to let you guys do more of the work, I think, than I will. What we're trying to show is that as we get closer and closer and closer to, I think I'm going to need 2 of these. As we get closer and closer and closer to 4, that the limit is getting closer and closer to the same thing. So I'm going to pick a value for x here, and here I'm going to pick x squared minus 3x. And I'm going to do the same thing over here. I'm going to make another table. And I need to approach this value of 4 from the left and from the right. So, for example, if I'm coming in from the left, I'll do that in the green, I need a number that's less than 4. So maybe I'm going to start with 3. And then I'm going to get closer. I'm going to put in 3.9, getting closer and closer to 4, right? Then I'll put in 3.99, and then I could put in 3.999. I keep getting closer and closer and closer to 4. On the right, which I'll do in red, now I need to get closer and closer and closer to 4, but I'm getting closer to 4 from the right-hand side, so I need a value bigger. So maybe I'll start with 5, and then I'll do 4.1, 4.01, 4.001. Okay? And all we're going to do is we're going to sub those values in. Now, to make more complete notes, you should probably sub in all of those. I'm going to save a little bit of time, though, if that's okay with you guys. I'm going to jump right to the last one, and hopefully I put it in the calculator okay. For this one here, I got 3.995001. So that looks like it's getting pretty close to 4. If I put in this one. And here I got 4. And of course, if you filled in the rest of the table, what you'd notice is that those values kept getting closer and closer and closer to 4. What's important as you look at it is that as we approach from the left, so the limit as x approaches 4 from the left-hand side, that's getting really close to 4. And that's the same as what's happening on the right-hand side. It's also getting closer and closer to 4. Which means if I jump back up here, the limit from the left is the same as the limit from the right, and your answer altogether is 4. Okay? Limits. It's all about this idea of what happens as we get really, really close to something, but we're keeping in mind it doesn't matter that we don't actually have to get anywhere. We're getting closer and closer and closer, but we don't have to get to the spot. Okay? Just get close.